What's up, everybody? Welcome to lecture 23, 24, something like that. It is over section 4.5. 4.5 is really just about one idea and one idea alone. What's this method of integration that's known as U-sub or U-substitution. And the Spark Note or Cliff Note version of this is just that it's really the chain rule, but backwards. It's the integration equivalent to the chain rule. That's all it is. And it can be summed up pretty easily by saying the integral of f of g of x times g prime of x with respect to x is equal to f of u du. What just happened? That went from ugly to, it's not totally bad. What? What's kind of being hidden here is that there's some steps in between. First, we're saying that u is equal to g of x. But that tells us then that du dx is equal to g prime of x. So we have that du dx times dx is equal to g prime of x dx, and we can think of that as du. So really we're just kind of obscuring some details just so that we can make the math a lot easier for ourselves. Now how the hell do we put that to practice? Like, how are we going to use that? Let's look at this example here. This example that I've got up here is the integral of x cubed times the cosine of the quantity x to the fourth plus 2. All of this is being integrated with respect to x. Well, if we look at this, it seems like the first step is to define a u, right? And if we look at the way u sub is described, u is equal to some interior function. So we look at this cosine for a little while and say, normally it's just cosine of x. So this looks like the candidate for our exterior and our interior function, right? This x to the fourth plus 2 looks like it should be our u. Well, if that's the case, then du dx is equal to 4x to the third, right? That's almost what we have. Well, if we do some rearranging, for example, if we move the differential dx to both sides, then we get 4x cubed dx is equal to du. It's not quite what we have though, is it? What we have is x cubed. So if we divide both sides by 4, we get that 1/4 du is equal to x cubed dx. And now we can use this to set up our u sub. Because we do have an x cubed dx, right? X cubed dx. We said u is equal to x to the fourth plus 2. So setting all of this up now, using u sub, where u is equal to x to the fourth plus 2, gives us that this is equal to the cosine of u du. That is equal to the sine of u plus a constant. And we know that u is equal to x to the fourth plus 2, so substituting that back in, we get the sine of x to the fourth plus 2, all of that plus a constant. And that's all there is to it. U substitution is quite literally just doing that. It's saying, let's find an interior function whose derivative exists outside. Let's substitute u in for that interior function. Then we're going to play with the derivatives until we get a differential in terms of what exists in our original integral. We're going to make that replacement, and then we're going to integrate. That's all there is to it. There's really not a whole lot going on. Having said that, let's look at one more example. Now in this example, we want to take the integral of the square root of the quantity 2x plus 1. We're integrating with respect to x. Our first step is going to be finding our u. And in this case, it seems pretty obvious, right? U should just be equal to 2x plus 1. But if that's the case, that tells us then that du is equal to 2 dx. But we don't have a 2 dx, do we? So we need to isolate just dx, and that tells us what our new substitution for dx needs to be. Well, isolating dx on its own, we have that dx is equal to 1/2 du. So by u sub, we have that this is equal to the integral of the square root of u times 1/2 du. We pull out that 1/2. And then this is the integral of the square root of u, integrated with respect to u. And from here, we can do everything the usual way, right? So this is going to give us, just writing all of this out now, 1/2 times the quantity, the integral of square root of u is going to be 2/3 u to the 3/2 power plus a constant. Multiplying everything through, we get that this is equal to 1/3 u to the 3/2 plus a constant. Now, once we evaluate this the rest of the way out, that is to say, once we substitute u back in, u is equal to 2x plus 1. That is equal to 1/3 times the quantity 2x plus 1, all raised to the 3/2 power plus a constant. And that's it. That's all there is to it. Let's keep chugging along. Now I'm going to wrap the lecture up here, but before I let y'all go, there were two things I wanted to touch on really quick. First, when applying u substitution to the definite integral, the result that you're looking for is going to require a combination of u substitution and the second part of the fundamental theorem of calculus. So in your notes where it says u sub for the definite integral, this resulting form is nothing more than u sub applied to the second part of the fundamental theorem of calculus. And that's it. That's really all it is. It's the same exact rules otherwise. Like all you're doing is just mixing and matching those two rules together. And there's two different directions you could take it to get to the same place, but they both get you there either way. So I just wanted to point that out. The second thing I wanted to bring up before I let y'all go is this idea of odd and even functions and how they interact with each other, or rather how they interact with themselves through the integral, through the definite integral. So first, in the case of an even function, if you were to integrate an even function about symmetric boundaries, so from negative a to a, then that integral with respect to x is going to come out to be 2 times the integral from 0 to a of f of x dx. Now a good example of an even function is x squared. Cosine is also an even function. And just to see that, test this property here. An even function is any function with this property. With this property that f of negative x is equal to f of x. Like I said, x squared and cosine are both really good examples of this. Now, in the event that a function is odd, so that is to say f of negative x is equal to negative f of x. Good examples of those functions, of odd functions, would be x cubed and sine of x. So if a function is odd, then its integration about a symmetric boundary, so from negative a to a, that integral will always come out to be 0. Now think about this for a couple seconds. See if you can see why this is true. And try graphing out these functions. What is it about these two properties that would make those two rules, or those two results, a thing? Why is this the case? Try drawing out a couple even functions and a couple odd functions, and see if you can find graphically, pictorially, geometrically, an argument for why that's happening. If you do that, I promise you, you're going to walk away from this chapter feeling a lot happier, because these two tricks can save you a lot of time when you apply them well. But having said that, there was nothing else I wanted to say. Please keep in mind you do have homework. I have released the rest of the homework, I believe. I'll have to double check that. But I believe all of your homework for the rest of the semester is out. Yeah, that's all I had to say. Have a good rest of your day. Have a good one, everybody.